Welcome to the video tutorial for gas laws. We'll begin with connecting our understanding of gases to the kinetic theory of matter. So remember that gases are small particles that move randomly with rapid velocity, and that we basically say, right, we said that the kinetic energy is much greater than the potential energy. So that there is, basically we can neglect any interaction between the gas molecules. And that the actual volume occupied by the gas molecules, right, the size of the molecules themselves is extremely small compared to the space between them. And then remember that the kinetic energy, as we increase the temperature, we're going to increase the kinetic energy of our gas sample. And last but not least, the gas molecules are in constant motion and they move rapidly in straight paths. So that if the gas molecules collide into each other, they're just going to bounce off like billiard balls and keep going. So now we're going to focus on the gas laws that we need to have for to be successful in our biology classes. So the gas law that we're going to look at first is Boyle's law. And this is about the relationship between the pressure and volume of gases. So this is a inverse relationship. If we have a gas system at an initial pressure and an initial volume, if we change the pressure, we're going to have to change the volume. And this is an inverse relationship. So that means that if we increase the pressure, we're going to decrease the volume, right? Or if we decrease the pressure, we're going to increase the volume. So the example that I like to give for you here is when we first started exploring deep down underneath the ocean, there's a lot more pressure at the bottom of the ocean than there is at the top. So we found some life forms down there, and these life forms were at a very high pressure. And the people were so excited to bring them to the surface that they brought them up right away. And as they brought them to the surface, there was less and less pressure, and guess what happened? The little organisms exploded, right? Their volume, right? As we had less and less pressure, the volume got bigger and bigger and bigger until it exploded. So that's kind of a gruesome example to help you remember. At a more personal level, it's how we breathe. So what happens when we breathe is we have the diaphragm. And as we take in a breath, the lungs expand and increase the volume. As we increase the volume, we decrease the pressure in our lungs, which allows us to inhale. So this is what creates our inhale. And then as we push back up on our diaphragm, then we decrease the volume and increase the pressure, and that's what creates the exhale. All right, so Boyle's law is a very important law for us to understand, because when we study the respiratory system, it's going to come into play. So let's look at an example of how we can tie a calculation of Boyle's law into our breathing. So the volume of air in a person's lungs is 615 milliliters at a pressure of 760 millimeters of mercury. So we can look and see by the language, right? So the milliliters tell us this is a volume, and the millimeters of mercury tell us this is a pressure. If you're uncomfortable with these pressure units, there is a video tutorial on pressure units that you can watch. Alrighty. So since these are the first ones we've looked at, we'll link them together. So the main thing, right? So this volume at this pressure, that's the important thing. The word at there helps us know that this volume is linked to this pressure. Inhalation occurs as the pressure in the lungs drops to 752. So these units tell us this is a pressure, and we already have one pressure, so this will be our new pressure. To what volume did the lungs expand? So this would be V2. Alrighty, so we have our calculation here, or our formula for Boyle's law, and we want to solve for V2. So in solving for V2, algebraically, that would be here. Okay, so we started with Boyle's law. We solved for the missing variable, and now it's plugging and chugging. So we plug in the values. Our pressure 1, 760 millimeters of mercury. Our initial volume, 615 milliliters. And then our new pressure, 252. So notice that, right, the millimeters of mercury, the pressure units cancel just like we would expect, and we're left with milliliters, which is a volume unit. So our calculation looks good. It's time to plug the data into our calculator and see what we get. Alrighty, so the volume of our lungs has increased to 621.5 milliliters, right? So as we increase the volume, we decrease the pressure, and that allowed the air to enter our lungs. And then, of course, since we're in class, the last thing we want to do is double check our sig figs. So we had 2 sig figs here, and 3 here, and 3 here. So our final result we should report would be to 2 sig figs. So the volume of our lungs would be 620 milliliters. Alrighty, so now we'll look at another important gas law for understanding our respiratory system, and that is Henry's law. So what Henry's law describes is that the amount of gas dissolved in a liquid is directly proportional to the partial pressure of the gas above the liquid. So basically, as we increase the pressure, right, of the gas, we increase the amount dissolved. And I think that's pretty intuitive. So, but let's make sure that everybody understands. So let's apply this statement. See if we can take this knowledge and apply it as wisdom. There are 2 unopened bottles of carbonated water that are at the same temperature. If one is opened at the top of a mountain and the other at sea level, which one will produce more bubbles? Explain your reasoning. Alrighty, so let's look, right? So here, if we have a can at 1 atmosphere, alright, so here's our can of soda. And then we have one at the top of a mountain. Let's say it's a really tall mountain, 14,000 feet. Alright, so here, right, there is a higher pressure, right, on the liquid inside the can. Here we have the lower pressure. Okay, so if we pop the tops, right, which one is going to produce more bubbles, right? The can at the higher elevation that's exposed to less pressure, right? So what's our explanation, right? So the lower atmospheric pressure, right, allows more CO2 bubbles to escape. Okay, you can think of the pressure as an invisible force field pressing down on the surface. So the high pressure at sea level, the gas bubbles would have to fight against that high pressure to be released, where here the gas bubbles have a much lower pressure to overcome, to escape. Alrighty, let's look at a couple more applications of Henry's law. Henry's law, there's not really a lot of calculations here. It's really more conceptual. So, for example, what happens to the solubility of oxygen gas in water in each of the following situations? The pressure of oxygen over the solution is decreased, right? So that would be similar to up above. As we decrease the pressure, then the concentration of oxygen in the solution, right, will decrease. Alrighty. So, and that's the solubility, right? So the solubility decreases as the pressure decreases. Alrighty. And then this one isn't really related to Henry's law, but I couldn't think of where else to put it in, so I put it here. Interestingly enough, when we have gases in solution, the results with temperature are the opposite of solids in solution. As we decrease the temperature of a solution, we increase the concentration of the gas. All right, and we can link that to the kinetic and potential energy. So if you're not familiar with kinetic and potential energy, there is a video tutorial to remind you. But as we lower the temperature, we lower the kinetic energy, and that allows more gas to dissolve in the solution. Alrighty. Okay, so that's our second gas law. We have one more gas law that's important to our respiratory system, and that is Dalton's law. Now, Dalton's law is the law of partial pressures. And so what Dalton's law tells us is that if we have a mixture of gas, which we'll describe as a P total, right? So the total pressure of that mixture is independent of the other gases. And basically, each gas behaves as if it was by itself in the container. So, right, so this would be the P total. This is describing the mixture. And then here would be the individual gases in the mixture. Okay, so we can take mathematically and we can use the partial pressures to determine the percent composition, right? The partial pressure of each gas can be calculated by multiplying the total pressure by the gas percentage, right? Or vice versa, if we want to find the percent of an individual, I think I spelled, yeah, okay. Start over. If we want to figure out the percentage of the individual gas, right, we would take the partial pressure of this gas and divide it by the total. So basically all I did was rearrange this expression so that we could calculate the percent of an individual gas. So, so the calculations for Dalton's law are pretty straightforward. We'll just do a couple here to make sure everyone's got the understanding. So we have a mixture of gases. There's nitrogen, oxygen, and helium present. and the total pressure is 760 millimeters of mercury. All right, so the P total is 760 millimeters of mercury. Now the partial pressure, the pressure of the nitrogen, is 120 millimeters, and the partial pressure of the helium is 240. Okay, what is the pressure of the oxygen? All right, so here we're going to use the top formula. So basically P total, right, is going to be P nitrogen plus P helium plus P oxygen. So the question tells us the total pressure and the pressure of the nitrogen and the pressure of the helium. So all we have to do is solve for the pressure of the oxygen. So we could simply take the 760 and subtract this here, right? So we would have 760 millimeters of mercury minus 360 millimeters of mercury. So we would have 400 millimeters of mercury. So that would be the pressure of the oxygen. Okay, sig figs here. We've done addition and subtraction. So our uncertainty is in the tens place. So we would want to put an overbar here, or we could use scientific notation to communicate our sig figs. Alrighty, and now we will use the other form of Dalton's law. Now that we have the partial pressure of oxygen, we can determine the percent of oxygen in the mixture, right? So the percent of oxygen will be the pressure of oxygen over the total pressure, right, times 100. I forgot to put that there. Okay, so in this case, we've determined that we have 400 millimeters of mercury of oxygen, and the total pressure was 760. So we can do the calculation. And we can find that we would have, our calculator tells us 52.6%. And looking at our data, we're at 2 sig figs, so 53% oxygen. Alrighty. So there are the three main gas laws that we need for understanding our respiratory system: Boyle's law, Henry's law, and Dalton's law of partial pressures. So now I would like to take on this last sheet here and tie this all together and show you how it applies to the gas exchange of our respiratory system and our blood. Okay, so here we'll use Henry's law, and mostly with a little bit of Dalton's. All right, so here are our lungs. And let's make sure everyone understands this chart. And then here is our heart. And then this represents our tissues, right? So inside our lungs, the pressure of oxygen is 159. And let's focus on oxygen first, all right? So use the diagram above to explain why oxygen diffuses from the alveoli in the lungs into the blood, and from the blood into the tissues of the body, right? So inside our lungs, we have a high partial pressure of oxygen. And if we look at the arterial blood, we see that the oxygen is only 100 millimeters of mercury. So as we look at the pressure of oxygen in the lungs, right, it's 159 millimeters of mercury. So it's going to force the oxygen into the arteries because they only have 100 millimeters of mercury. Okay, so now that arterial blood, it's been oxygenated, right, by the pressure of the oxygen forcing the oxygen into the arterial blood, and then the blood's traveling along until it gets to our tissues. And then notice in our tissues, right, our tissues only have 30 millimeters of mercury of oxygen. So that 100 millimeters of mercury of oxygen is the oxygen is going to flow into the tissues. Now let's look at the return trip. When we look at the return trip, we're focusing on the CO2. Well, the cells inside our body are busy undergoing aerobic respiration and producing CO2. So if we look at the pressure of CO2 in our cells, it's very high. I can almost fit this. Okay, so we have 60 millimeters of mercury of CO2 in the tissues. So as that blood comes by, it deposits the oxygen, and then now it becomes venous blood. And notice here's the oxygen, the CO2 here is only 46 millimeters of mercury. So that high CO2 level in the tissues drives the CO2 into the blood. That's now the venous blood. And then that venous blood goes up to the heart and then travels into the lungs, where the pressure of the CO2 is incredibly small at 0.3 millimeters of mercury. And so that's how we expel the CO2 out from our lungs, from our tissues. So I hope that you have found this video tutorial helpful on gas laws, and that you'll take the time to work a few homework problems to reinforce the concepts.